So, today we will discuss few problems on continuity, differentiability and application of the derivatives like a mean value theorem, monotonically increasing and decreasing function, so on. But prior to start with the problems, we will take up the topic which we have not covered in the last lecture, that is the Taylor's theorem. So, before that we will first complete that proof of the Taylor's theorem, and statement we have already discussed, but still we rewrite again. This Taylor's theorem is also known as the generalized mean value theorem, and this says if a function f and its derivative up to say order n plus 1 or up to n minus 1 are continuous, up to order n minus 1 are continuous, up to say order n, let us we take up to order n plus 1 are continuous, and continuous over the closed interval, say a to a plus h, okay, this closed interval a b, and differentiable and its derivative and its nth derivative that is fn x. So, here fn x nth derivative exists in the open interval a to a plus h, then there exists at least one number theta lying between 0 and 1, such that the expansion of this function at the point a plus h can be written in the form of a series f a plus h f prime a plus h square over factorial to f double dash a plus h n minus 1 over factorial n minus 1 f of n minus 1 a plus h n over factorial n f n a plus theta h, this expression. So, a function f can be expanded in the power of h, in this form, and the last term is called the remainder. Basically, it is called the Lagrange's form of the remainder. This is called the Lagrange's form of the remainder. There are various forms, we are not interested in the other, just log. Now, here last time we have also in the last lecture we have taken in a similar statement, because it coincides with the previous. If I choose another form, or we can say of this statement is, if suppose I take f a plus h and let x be a point of the interval a to a plus h, okay, a to h, and let f satisfy the conditions of Taylor's theorem as defined above. As defined above. In the interval a to a plus h, a to a plus h, okay, so that it satisfies the condition for a to x also. Okay. Then if I take a plus x, then the equation 1 can be rewritten in this form. Then equation 1 can be written as f of x equal to f a plus x minus a f prime a plus x minus a whole square over factorial to f double dash a plus so on up to say x minus a to the power n minus 1 factorial n minus 1 f n minus a n minus 1 derivative at the point a plus the remainder term r n x, where r n x is as x minus a to the power n divided by factorial n nth derivative at a point a plus theta x minus a, where the theta lying between 0 and 1. Then one can be written in the form this, where h is taking to be as x minus a. So, if in this form, if I take h to be x minus a, then the function is well defined. Function is throughout continuous. Its derivative up to order n minus 1 is continuous over the closed interval a b, and f n plus 1 f n exist. It means they are also differentiable over the open interval a b. When we say f n exists, means the derivative up to order n exists in the open interval a to a plus h, and they are also continuous over the closed interval a to a plus h. Then what he says is, if we picked up any point in the interval a b, so I am taking the point like a corner point x plus h. In fact, this will be a b interval, where I choose a point x in between a b, and that point is a plus h. Then expansion of the function f x in the powers of x minus a, ascending powers of x minus a, can be expressed in this form, where the first n terms is the series and the last term, the nth plus 1th term, that is equal to nth term, is the remainder term, and which called the Lagrange's form of the remainder. And this point is obviously a point, clearly the point a plus theta x minus a. Since theta lying between 0 and 1, so obviously this point belongs to the interval a to x, because it cannot be a, because theta is not 0. It cannot be x, as theta is not 1. Okay, so it lies in between this. So there is some point in between the interval where the remainder term can be expressed. Okay, the proof of this, which we have not done it last time. Let us see the proof. Its proof is simple. In fact, what we do is we construct a function such that so that we can apply the Rolle's theorem, and once you apply the Rolle's theorem, a point c can be obtained where the derivative becomes 0, and from here the remainder term will come. Okay, so that is our idea of the proof. So, let us consider the function phi x as f x plus consider function phi f x plus a plus h minus x f prime x plus a plus x minus x whole square y factorial to f double dash x and so on, plus a plus h minus x to the power n minus 1 factorial n minus 1 f n minus 1 x plus a plus h minus x power n, where a is a constant, where a is a constant to be determined such that the value at the end point of phi, that is phi a is equal to phi a plus h. We put the restriction on phi in such a way so that a can be computed. So, suppose I put this restriction and then from here let it be 2. In the 2, if I replace x equal to a and x equal to a plus h, what we get? As soon as you substitute x equal to a plus h, all the terms gets cancelled except you are getting f a plus h. So, we get f of a plus h, and when you take x equal to a, then what you get in the right hand side, we get f a plus h f prime a plus h square by factorial to f double dash a and so on, h to the power n minus 1 factorial n minus 1 f n minus 1 a plus a into h to the power n. Okay. So, this function. Now, the function phi is a continuous function. Since the function phi is continuous over the interval a to a plus h and differentiable in the open interval a to a plus h, and also satisfy the condition phi of a equal to phi of a plus h. Why? If you look the function phi is basically is a linear expression, is an expression which involves the function f x and the term a like L minus x or L minus x square and so on. So, instead of the one x to the power n and the derivative, since function f x and its derivative of 2 orders a n minus 1, they are continuous, and this x to the power n type a alpha x plus beta x to the power n type, they are continuous function. So, product of each term will be continuous. So, phi will be continuous. Similarly, phi is also differentiable, and at the end point of the interval a and a plus h, it attains the value same value. So, we can apply the Rolle's theorem. So, by Rolle's theorem, there exists a point C. So, there exists some theta, there exists theta lying between 0 and 1 such that the derivative of the function at some point a plus theta h is 0. So, a plus theta is a point lying between a to a plus h. Okay. But what is the phi prime x? What phi prime x, if we just go and differentiate it, you will get many terms get cancelled, and only you are getting differentiation of this one term when its derivative is here and this, and rest is telegraphically it gets cancelled. So, we get finally the value is a plus x minus x, a plus h minus x to the power n minus 1 factorial n minus 1 f n x minus p in minus n a plus h minus x to the power n minus 1. This you get. Now, this quantity at x equal to a plus theta h, the phi dash of this number is 0. So, from here what we get? We get h to the power n minus 1 minus theta n minus 1 over factorial n minus 1. Just substitute this value x equal to this number into f n a plus theta h minus p n a 1 minus theta n minus 1 h to the power n minus 1. So, if we solve it, we get the value of a will come out to be the thing that is 1 by factorial n f n a plus theta h, where the theta lying between 0 and 1 minus theta is not equal to 0 and h is not equal to 0 and h is also not equal to 0. Okay. So, we get the remainder a and then substituted this value in 1. So, put in 2, we get the result proof with the remainder term. Okay. Now, as a particular case, we can say when a is equal to 0, then the Taylor series, Taylor's expansion or Taylor's theorem reduces to reduces to the expression which is f x equal to f 0 plus x f prime 0 plus x square over factorial to f double dash 0 and so on, x to the power n minus 1 factorial n minus 1 f n minus 1 0 plus the remainder term, that is x to the power n over factorial n f n theta x, and this form is known as the Maclaurin's theorem. Maclaurin's theorem. Okay, this we get this. Now, further, if the remainder term, that is Rn, which is basically equal to h to the power n or x minus a to the power n over factorial n, x to the power n over factorial n, f n a plus theta x minus a plus theta x minus a. If this remainder term goes to 0 as n tends to infinity, then Taylor's theorem gives the Taylor expansion of the function f x, at the point x, at the point x or around the point 0, of course, around the point 0, at 0, Taylor expansion, at the point x minus a, at the point a, around the point a, around a in the power of x minus, and the Maclaurin's theorem give the corresponding Maclaurin expansion of the function around the point 0. That is what you get it. Okay. So, for example, suppose I take the function f x equal to e to the power x. Write down the Maclaurin's expansion of this function, Maclaurin's expansion. So, what is our derivative? If I differentiate n times of this, is nothing but the e to the power x itself. So, this is true for every x belongs to R. So, when you take the 0, it is 1. That is, use the now Maclaurin's expansion. The Maclaurin's series expansion, let it be 3. So, when you use the 3, so use 3, you will get the expansion as 1 plus x square y factorial 2 and so on, x to the power n minus 1 factorial n minus 1, and then you will get the remainder term, and the remainder term will be what? X to the power n over factorial n e to the power theta x, where the theta lying between 0 and 1. Okay. But if the remainder term goes to 0, then we get the Maclaurin's series or expansion of the function e to the power x. So, here the remainder term is x to the power n over factorial n e to the power theta x. Now, if you look the e to the power theta x, now e to the power theta x, if I take this, since e to the power theta x, the value of this, if it is theta x is positive, then the value will be, that value is less than e to the power x if theta is positive. Sorry, if x is positive, because if x is positive and theta lying between 0 and 1. So, e to the power x, e to the power theta x will be less than e to the power x. And when x is negative, then it is coming below. So, it is dominated by 1 always. If this, it means the e to the power theta x will always be a bounded function by e to the power x. Okay. So, it is bound, and x to the power n by factorial n, limit of this as n tends to infinity will be 0. Why it is 0? Because the reason is, when it for x is fixed, for fixed x, we can identify there exists an n such that mod of x is less than capital N. So, we can find x to the power n factorial n as x over 1, x over 2, say x over n, and then you are getting x over n plus 1 up to x over n. So, what happened? These are the finite values, and this value, so some alpha into x over, say this number, every term will be less than n. So, we can write x by n raised to the power n minus 1. So, this is less than 1 mod of this. So, this will be tending to 0 as n tends to infinity. So, this will go to 0. So, therefore, the remainder term in this will go to 0. So, expansion of h to the power x will be 1 plus x square factorial 2 plus x to the power n factorial and so on. And this will give the Maclaurin series for this. This is the Maclaurin series for the function f x, which is e to the power x. Okay. Similarly, if we take the write down the Maclaurin's expansion of the function f x equal to, say, sin x. Okay. Now, we know the derivative of the sin x, the nth derivative of sin x is comes out to is sin x plus n pi by 2, and this is true for every x belongs to R. Okay. So, take the x is 0. So, what you are getting is sin n pi by 2. Now, when it is n pi by 2, it depends on n. Okay. So, for n is even, when you are taking, it becomes pi for 2 pi etc. So, we are getting the sin x, is it not? And then the x plus theta. So, this the value of this will be 0, and for n are odd numbers, the value will be sometimes plus 1 or minus 1. So, if you use the 3, we get the expansion sin x as x minus x cube by factorial 3 plus x 5 by factorial 5 and so on like this. And what is the remainder term? R n x, the remainder term R n will be x to the power n y factorial n sin of theta x plus n pi by 2. This is the remainder. So, mod of remainder, mod of this, but this limit and where remainder term is this, which is dominated by mod x to the power n by factorial n less than or equal to this, because this is always less than or equal to 1. So, as n tends to infinity, this will go to 0 as n. So, again we can expand it and get the series expansion for the function. So, that is what is 1 minus x, and the second derivative of the function phi prime is negative in the interval 0 less than x less than equal to x less than equal to 1, then so that phi is an increasing function, phi increases of phi x increases in the interval 0 less than equal to x less than equal to half, and decreases in the interval half less than equal to x less than equal to 1, hence attains maximum at x equal to half. Okay. Let me see this. What is given is, let function f is well defined function over the interval 0 and 1, and second derivative is negative. So, function is giving to be function f is continuous, differentiable and the second derivative exists, which is less negative in the interval 0 less than x less than equal to 1. So, this much information is known. Now, let us consider the phi dash x. Phi dash x. If we take the phi dash, this is the f prime x and the derivative of this is f prime 1 minus x and derivative of minus x is minus 1. But we cannot get any information whether f prime is greater than this or not. Okay. So, go for the another one phi double dash x. So, phi double dash x comes out to be f double dash x and this comes out to plus f 1 double dash minus. Now, from here we claim that phi double dash x is negative for x negative. Why it is negative? For x belonging to the interval say yes. Now, here we say here this is okay. Why f double dash x is negative in the interval this when x varies from 0 to 1. So, since our f double dash x is negative for all x belonging to the interval 0 1 close interval. So, f double dash 1 minus x will also be negative. Why? Because when x is from for every x, because this is when x varies from 0 to 1, then 1 minus x will vary from 1 to 0. So, they always lies in the interval 0 1 and for all point which lies in the 0 1 the second derivative is negative. So, phi double dash is negative for all x in the interval 0 1. Okay. So, this is information we have got it. Achha, now, we can come now x varies. Okay. So, what we get is the phi dash x. So, our once so phi double dash x is negative. Therefore, phi dash x will be a decreasing function monotonically decreasing function. So, once it decreasing over the interval 0 to 1. Okay. Now, let me see what is that decreasing function. So, the value of the function at the point 0. So, what is the value of the function at the point 0? The value of the function at the point 0 is f 0 minus f prime 1. The value of the function at a point half phi dash a at the point half is nothing but what? Phi dash half, this becomes what? When you take f prime 1, this is 0, f prime half minus f prime half which is 0 and then value of the phi dash at the point say 1. What is this? F prime 1 minus f prime 0. So, what is this? This is the function phi dash. Phi dash is this function which attains the value this is 1 interval, this is half. So, phi dash attains the value 0 at this point and then these values at the point 0 is this value, at the point 1 this value. Now, phi dash and phi dash a they are differing by minus sign only, because minus times of this number is the second. So, if it has a positive value here, this will have a negative value here, and if it is negative value, then this has a positive value. But phi dash is a decreasing function. So, phi dash is decreasing means it cannot go from negative to positive. So, what we get it that since it is monotonically decreasing. So, we can consider from here is that in between 0 to 1 phi dash must be positive. So, here it should be positive, here it should be negative, and there, so that it decreases and cross the x axis and going down. So, this shows that the function phi dash x is negative for x belonging to the interval 0 to half and positive for all x belonging to the half and 1. It means this implies the function phi. What is the function? Therefore, our function phi is a phi function is decreasing in the interval 0 to half and increasing. No, it's wrong. It's other way around. Sorry, it's other way around. This is positive. This is greater than 0 in this interval, and this is less than 0. So this is increasing function in the interval positive. So it is increasing. This is what it's coming. No. It's I'm sorry. What is this? Is this function phi dash? If it is positive, it is increasing. Oh yes, and then it is decreasing. So function will be something like this, and then at the point half, it is coming to be at the point half. What is this? Is yes, at the point half. So it is decreases, is it not? So it will go like this. So maximum value will come at the point half. Yes, so we get this. So this is our increasing in this and decreasing in the interval half to 1. So our function f phi which is this function f x. So what we get is the phi x increase in this, decrease in this, and attains the maximum value at x equal to phi. So phi at x equal to half, it will attain its maximum value, is it not? Because then only we are getting the function phi dash is this 0 and this one is 1. So here it is f dash 0, and then f dash 0 is greater than this, f dash 0 is greater than this, and this is negative. That is why it is coming. So it is coming to be just like that. Okay. So we get this one, the value at the point this is basically like at the point x equal to half, this function is this. So what we get is that increases in the interval. So function phi is increasing in the interval this, phi dash x is greater than 0 and this is less than 0. Okay. So we get this one and the phi dash x. Okay. So this shows our result is complete. Okay. So that complete the result. Right, something is wrong.